Pluto is a far-off and confounding minor planet, once an individual member of our planetary family. However, continuous disturbing articulations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning revelation. They suggested that this chill world is on an intensive collision course with Neptune. But how could this happen, and what may be the consequences of such a fundamental event? Are we seeing a flabbergasting impact or erraticism, or is there something more to this oncoming endless impact? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was scaled down to a dwarf planet, is significant because of its odd orbit. It remains a subject of interest and study in the scientific community, as shown by recent theories by leading experts. Pluto's orbit is perilously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous accident between these two planets, which would pose a gigantic risk to Earth. But how is such an event even conceivable? Pluto's trip around the Sun is unlike that of any other planet in our solar system. It requires a complex 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even finished one full revolution yet. The intrigue doesn't stop there. Pluto's orbit is marked by its unusual elliptical shape, drifting far from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is significantly more extreme compared to other planets. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, opposing what we would expect based on their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to determine its unique orbit. Unlike other planets, whose orbits lie close to the ecliptic plane, Pluto's orbit stood out because of its steep inclination and elliptical shape. The mystery grew with the realization that Pluto's orbit indeed crosses Neptune's. Despite these complexities, Pluto's orbit has remained stable over long periods of time, preventing a collision. This stability is due to the complex interplay of gravitational forces, particularly from the giant planets like Neptune, Jupiter, and Saturn. Jupiter's enormous gravity is strong enough to keep Pluto on a steady path for potentially billions of years. These factors are crucial in maintaining order and preventing chaos in our solar system. Pluto's orbit is a striking example of celestial mechanics at work, demonstrating both stability and turbulence in our solar neighborhood. The exceptional characteristics of its orbit, influenced by the gravitational forces of nearby planets, particularly Neptune, highlight the complicated and dynamic nature of space. Predicting significant events, especially involving erratic orbits like Pluto's, presents major challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainty. While mathematical simulations provide a robust means for understanding and predicting the future behavior of celestial bodies, they also reveal the limitations of our predictive capacities. So why are notable astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune, despite the complex forces working to prevent such an event? Neil deGrasse Tyson and Michio Kaku, both prominent figures in cosmology, have expressed concern about a potential crash between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a dazzling and catastrophic event in our solar system. The impact would release an enormous amount of energy, likely obliterating Pluto due to its smaller size and cold structure. Debris from the impact could scatter across the nearby solar system, potentially introducing risks to other planets and their moons. For Neptune, such an impact could alter its current environment and possibly even its orbit, depending on the specifics of the crash. Michio Kaku, a notable theoretical physicist known for his work in string theory, offers an intriguing perspective on the potential impact. His insights into the future of space exploration and the relationship between celestial mechanics and theoretical physics provide valuable understanding of the phenomena surrounding Pluto's orbit. Understanding the complex gravitational interactions and orbital mechanics of celestial bodies like Pluto could yield crucial information for future space missions. This knowledge could help in exploring the solar system more effectively, anticipating potential risks, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a guide to how we may approach and understand distant worlds in planetary science, celestial mechanics, and theoretical physics. These fields are deeply interconnected, as the movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to key principles of physics. If Pluto and Neptune were to collide, it would be a fantastic event in cosmology, offering an exciting observational opportunity that could potentially connect with string theory. String theory, a hypothetical framework where point-like particles in particle physics are replaced by one-dimensional strings, seeks to explain the fundamental forces in matter and the universe. The impact could create extreme conditions of energy and gravity, potentially leading to conditions where predictions made by string theory could become detectable. For instance, the high-energy impact could provide insights into the behavior of key particles and forces under extreme conditions, which is a crucial area of interest in string theory. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be immense. It could potentially add to our understanding of the fundamental nature of the universe, as described by string theory and other areas of theoretical physics. Pluto's peculiar dance around the Sun continues to captivate scientists and enthusiasts alike, offering a window into the intricacies of celestial mechanics. While its reclassification as a dwarf planet sparked discussion and reshaped our understanding of planetary bodies, recent revelations about its orbit have reignited interest in its role within the solar system. Neil deGrasse Tyson and Michio Kaku, two prominent voices in space science, have raised concerns about a possible impact between Pluto and Neptune, shedding light on the complex forces at play in our cosmic neighborhood. Their warnings underscore the importance of understanding the gravitational interactions and orbital mechanics that govern the movements of celestial bodies. Pluto's orbit, marked by its unpredictability and steep inclination, defies traditional assumptions and challenges our perspective on planetary motion. Unlike the nearly circular orbits of its neighboring planets, Pluto's path follows a unique course, crossing Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, especially Neptune, plays a significant role in shaping Pluto's orbit and maintaining its stability over many years. Despite the tumultuous nature of its path, Pluto's orbit remains relatively stable within the broader context of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as suggested by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and unpredictability in planetary dynamics. While such an event remains speculative and highly unlikely in the near term, the gravitational dance between Pluto and Neptune emphasizes the delicate balance of forces that govern celestial bodies within our solar system. Beyond its scientific significance, the study of Pluto offers practical insights for future space exploration missions. NASA's New Horizons spacecraft, launched in 2006, provided astounding pictures and data of Pluto and its moons during its historic flyby in 2015. The mission uncovered remarkable details about Pluto's surface features, including vast fields of water ice and broad plains of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet. The success of the New Horizons mission highlighted the technological advances and collaborative efforts necessary for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the environmental conditions present in the outer reaches of the solar system. These revelations have implications for future missions to explore other dwarf planets and trans-Neptunian objects, helping us understand planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the criteria used to define celestial bodies within the solar system. The debate over planetary classification reflects broader questions about scientific taxonomy and the evolving nature of astronomical knowledge. While Pluto meets several criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, Its classification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Embracing Pluto's orbit expands our understanding of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are essential for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary motion and the development of the Kuiper Belt, a region beyond Neptune populated by small icy bodies. Examining Pluto's orbit offers clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system's development. Understanding the complexities of celestial mechanics can also inform future space exploration missions, including the search for habitable worlds beyond our solar system. By studying the movements of distant celestial bodies, space scientists can identify potential targets for future exploration and assess the feasibility of traveling to other star systems. The potential impact of a Pluto-Neptune crash, while highly unlikely, serves as a reminder of the dynamic nature of the universe and the unpredictability of large-scale events. As we continue to explore the outer reaches of the solar system and beyond, the study of planetary orbits and celestial mechanics will remain a central focus for astronomers and space agencies alike. Pluto's orbit, which deviates significantly from the paths of other planets, offers valuable lessons about the complexities of planetary motion. The stability of its orbit over long timescales, despite its unpredictability, provides important insights into the balance of forces that govern the movements of celestial bodies. In a sense, the ongoing study of Pluto's orbit and its potential interactions with Neptune reflects the broader challenges of understanding the universe at large. With each new discovery and each theoretical model, we continue to refine our knowledge of the universe, uncovering the mysteries of distant worlds as we explore the depths of our solar system. Pluto remains one of the most fascinating objects due to its unique characteristics. While many may think of Pluto as a distant, frozen world with little significance, its study has brought to light many important insights about our solar system's formation, evolution, and the nature of planetary bodies. The fact that Pluto was once considered the 9th planet and then reclassified as a dwarf planet opens up broader discussions on how we define planets and celestial bodies. This ongoing debate challenges our understanding of the solar system, particularly as new objects in the Kuiper Belt, such as Eris, Haumea, and Makemake, reveal that Pluto may not be as isolated as once thought. Rather, it belongs to a larger family of icy worlds far beyond Neptune, suggesting a much more complex and varied outer solar system. Pluto's orbital characteristics provide a rich source of information for scientists. Its orbit is not only highly elliptical but also highly inclined compared to the orbits of other planets. This means Pluto's distance from the Sun varies drastically throughout its orbit, affecting its surface conditions and potentially its atmosphere. Unlike the other planets that orbit relatively close to the ecliptic plane, Pluto's orbit, tilted at an angle, crosses the plane at a sharp angle, creating a dynamic and unpredictable path. This instability is what makes the potential for interaction with Neptune so intriguing. As these two bodies come close to each other in their respective orbits, the likelihood of gravitational interactions that affect both planets increases. Despite the oddities of Pluto's orbit, it is this very eccentricity that allows scientists to study the gravitational forces and mechanisms that control the orbits of celestial bodies. The interactions between Pluto, Neptune, and the giant planets further demonstrate how gravitational forces shape not only orbits but the overall structure of the solar system. Even small changes in the orbital parameters of planets can lead to large-scale shifts in the system, highlighting the delicacy of the cosmic dance in which these bodies engage. The presence of many icy bodies in the Kuiper Belt also raises questions about the potential for future space exploration. The region, which extends far beyond Pluto, is home to numerous objects that could offer new opportunities for scientific discovery. Some of these objects, like the dwarf planet Haumea, are thought to have characteristics that may resemble the early solar system. Exploring these objects could provide crucial insights into planetary formation processes. Furthermore, These icy bodies hold the key to understanding the volatile and dynamic processes that shape the outer edges of our solar system. In addition, the discovery of other dwarf planets and trans-Neptunian objects has helped astronomers refine their understanding of the solar system's evolution. As technology advances, more and more of these distant objects are being detected, each offering a glimpse into the past of our cosmic neighborhood. Understanding the gravitational influences and interactions that occur in these outer reaches of space may help us predict how the solar system could evolve in the future. Moreover, the study of Pluto and the surrounding region could yield information on the potential for life beyond Earth. While Pluto itself is inhospitable, the study of other moons and objects within the Kuiper Belt may reveal clues about the conditions necessary for life to arise. These distant worlds may have environments vastly different from our own, but their study could deepen our understanding of the requirements for life and its potential existence elsewhere in the universe. In the coming decades, we can expect more groundbreaking discoveries as missions like NASA's New Horizons continue to send back valuable data. The scientific advancements in planetary science, celestial mechanics, and astrobiology will only expand our comprehension of Pluto's role in the larger cosmic context. As we continue to push the boundaries of space exploration, Pluto's place in our solar system remains a subject of deep fascination and mystery, contributing to our quest for knowledge about the universe and the origins of our planetary system.